Okay. All right, this is a very pictorial view of the LISA spacecraft, in that we have 3 spacecraft. Each of them has 2 test masses, and that's a choice I'm going to talk a little bit more about later. But we bounce the laser beam. Let's see, the incoming laser beam from this spacecraft hits that test mass and is compared to the light that's going out from that. So we have these 3 different arms. And because the spacecraft orbits cause changes of these distances a function of time, then the distance here and the distance there are not going to be the same. And so we don't have an equal arm Michelson interferometer, and we can't just compare this round trip beam to this round trip beam on a photodetector and get a very nice phase readout. So I'm hoping Bob's going to talk more about this, and then John on signal processing is going to talk more about this. But I wanted to give you just a flavor for it now. What we have on each spacecraft, if you think about one spacecraft being the central vertex point, then we're going to have 2 photodetectors. That should be S2. Sorry, S1 and S2 are the photodetector outputs that are the signal as a function of time. The laser, we're going to measure phase as a function of time. And that signal is going to have the laser phase noise, a round trip light time earlier, minus laser phase noise now, which is what you get out of Michelson, plus the noise, plus the gravitational wave signal modulated on top of those. And the problem is the laser phase noise is many, many orders of magnitude larger than the signal that we're trying to receive, about a factor of 10 to the 10th. So how do we have to measure this signal and measure that signal, S1 and S2, and cancel them somehow. And so this is a crude way of doing the laser signal processing that will be talked about more later. You do a Fourier transform of one of the signals to get the Fourier transform of the laser phase noise plus these other things. Then you can estimate from one arm what the laser phase noise is. Just treat that as a known arm and just say the signal is due only to laser phase noise. So you make an estimate that has this shape. That should have the laser phase noise in it. That's what happens when you do this in the morning before the talk, is you forget something. There should be a P of F here. Okay, and then you form another signal estimate here, S1, which is this P times this factor. Then when you differ the Fourier transform of the 2 signals minus these other estimated quantities, you get something that I call capital P, capital N, capital H. H is very much the gravitational wave signal. P is the laser phase noise times this factor. Okay, so this is the factor that we have to cancel out the laser phase noise. And it has the length of arm 1, the length of arm 2. Delta L2 is how well we know the arm length, and the arm 1 and arm 2. So how well do we know the distance, absolute distance, so that when we're making this time comparison and signal processing, how much of an error do we have in doing those time comparisons? Divided by one of the lengths. This analysis assumes the lengths are about the same, times this 4 pi I F over C. So this is the factor that we're going to have to cancel laser phase noise. So how big is the laser phase noise? Well, a nominal number we're keeping is sort of 30 hertz per root hertz in terms of power spectral density of the laser frequency noise at a millihertz. There's a lot of numbers kicking around, but they're like that. Question?
Why 30 hertz per root hertz and not 30 root hertz?
30.
Why the unit is hertz per root hertz and not just root hertz?
If you're measuring frequency as a function of time and did the power spectrum, or did a Fourier transform of that, the frequency as a function of time is hertz. Power spectrum, or the Fourier transform, will give you hertz squared per hertz. So this is the square root of that, which is hertz per root hertz.
It's conventional always to quote spectral density of anything is something per root hertz.
Something per root hertz. So I could divide by the laser frequency and get a fractional frequency as a per root hertz, and that would be dimensionless per root hertz. So is it the per root hertz that's peculiar, or is it the hertz per root hertz? Why don't I simplify it?
1 over root 2 is
okay.
Root 2 over 2.
Well, the answer is because
that was the question.
Okay. The answer, this is just the way I think of measuring frequencies as a function of time, Fourier transforming, and then I'm going to divide it by the observation frequency of interest times the wavelength to get meters per root hertz. Okay, so in the end, what I care about is meters per root hertz divided by the arm length, gives me gravitational strain. So this number, so 30 hertz per root hertz is just a conventional number people kick around as an attainable goal. That gives us 5 millimeters per root hertz of distance noise, and we really like 10 picometers per root hertz shot noise, and so we have to cancel this by something like a factor of 10 to the 9th. Okay, so that has 2 consequences. One is that means this factor has to be 10 to the minus 9th. which is reasonably achievable for a millihertz if we know the distances to 20 meters. So we need to know the distance between spacecraft to on order of 20 meters. And that's not too hard. But it also means we have to be measuring these two time streams with precisions of parts in 10 to the 9th. Okay? Which is a little bit better than things that we've done before. Okay? So to get to 10 picometers per hertz, that means we have to measure the laser phase to about 10 to the minus 5 of a cycle, because a cycle is 10 to the minus 6 meters. So 10 to the minus 5 cycles times 10 to the minus 6 meters is 10 to the minus 11 meters. So we have to be able to measure the laser noise to 10 to the minus 5 of a cycle or better. The GRACE spacecraft is flying sort of a modified GPS receiver to measure spacecraft to spacecraft distance using microwaves. And they're using a much longer wavelength, but with the same measurement scheme we could use for LISA using the photodetector instead of the microwave receiver. They're doing 10 to the minus 4 cycles per hertz. So we have a little ways to go in terms of the phase measurement, and then we have to do this cancellation procedure, which you'll hear more about in another talk on signal processing. Okay, so that's what I meant to say about orbits, orbital geometry, the effects of orbital geometry on the system design, pointing, frequency, things like that. So now I'm going to show you some pictures of kind of what the spacecraft looks like, and eventually the point is to see why it looks like it is, why are we limited to a 30 centimeter telescope, how are the signals routed around, things like that. So this is a picture of the spacecraft, and the blue here is meant to indicate solar panels. There will be a cover here that's not shown that would keep sunlight from hitting the spacecraft. So there's at least some kind of thermal shield over the top, and it may or may not have solar panels all across the top. I'm told the photocells are more efficient in the red, which is why they scatter blue better, so they look more blue, although all the ones I've seen look black. But I'm told they look blue, the ones for the real spacecraft. So inside the spacecraft, there's a bunch of equipment that's not shown here, but we have this Y-shaped tube. Okay, and inside the Y-shaped tube, we have 2 telescopes and the rest of the measurement apparatus. So I'm going to talk a little bit later about thermal isolation. We have thermal noise problems from a lot of different sources. So the sunlight is our biggest unremovable source of thermal fluctuations. So that to first order, that's shielded out by having a cover. Okay, but the inside of this cover is going to thermally radiatively couple to this Y-shaped payload tube, and then that in turn is going to radiatively couple to what's inside there. Okay, so what we're trying to do is have the spacecraft and its shield be the outer stage of a 3-stage thermal filter. The Y tube here will not be not in good thermal contact with the spacecraft. It's actually going to be thermally isolated from the spacecraft shell, which places constraints on how this is mounted, because it has to sustain launch vibration as well as being thermally weakly coupled. So that's an intermediate stage, and then inside that there's another cylinder around the key parts of the payload. So there's a 3-stage thermal isolation filter in here. This is a picture of the ESA spacecraft study that shows a little more detail. Here they're showing the cover, and on top of it they have 2 radio antennas for sending data back to the Earth. Currently we're thinking these antennas are going to be repointed once a week or so, and that causes a lot of people nervousness. But the only alternative that I know of, I guess there's some new alternatives, so maybe you can talk about that. Okay, so there's that Y-shaped shield. The ESA company put this triangular arrangement here to carry the load of all the equipment, and these boxes floating in space would actually be rigidly attached to either these panels or the cylindrical wall, which is not shown here. We need things like star trackers, a computer, a radio system, et cetera, et cetera. And then attached to the bottom of this on launch would be a propulsion module. To get into the orbits that we want, the launch vehicle can get us into an orbit to drift away from the Earth. But to get into the orbits that we eventually want to stop drifting away from the Earth, so that we're always about the same distance behind the Earth. And before we do that, we want to change the inclinations of the orbits so that they're tilted with respect to the ecliptic plane. And so to try to do that in as low a cost as possible, where part of the cost is the cost of the launch vehicle, we're planning to use ion engines, like the New Millennium program, Deep Space One, that just flew by the nucleus of a comet, uses an ion engine. It's much more mass efficient. So this little stage here has chemical propellants for doing attitude control while these ion engines are firing. but we're reasoning that once we get on orbit, we don't need these fluids sloshing around near our very sensitive test masses, and so we'll just jettison them. Whether that's not necessarily has to be, but otherwise we have to make sure these things are very stable by venting their propellant out to space or something like that. So that's a trade study that's currently going on, but this is the nominal. So we want to have 3 of these, and we want to have them reasonably inexpensively. So we want to launch them on a launch vehicle that will carry enough mass out there as inexpensively as possible. So the launch vehicle that we've designed to is a Delta II launch vehicle, which you guys don't care about. But what's important is it has an inside diameter of 10 feet, which is about 2.9 meters or 2.7 meters, and it has an available height that's limited. Okay, you can use this volume up here, but then it can't be symmetric with things down below. So what we've done here is stack 3 spacecraft on here to try to fill as much of the volume as we can with 3 identical copies. Okay, and doing that and knowing the size of the ion engines and the available height then gives the height available for the telescope. Okay, so that 30 centimeter fits in there. Okay, but a 1 meter mirror won't. Okay, so that's where we're stuck right now. Right now, the mass of this is I don't know, within 10% of the capability of this rocket to launch it. And that level of margin is uncomfortable for most space people. And so probably this will end up being launched on a bigger launch vehicle, which means much more expensive launch vehicle. But so maybe this mirror size will get bigger. But
what's about the Delta II that they thinking about using?
Well, it turns out there's something called a Delta III, which isn't surprising. And that allows you to have twice as much mass for about 10% more cost. The problem is there aren't enough customers of that, so they're not going to make any more of those after 2007. So then they're going to make Delta IVs. Okay, the Delta IV family I don't know too much about yet, but they'll have a range of sizes and capabilities.
We're still thinking about American launchers for this.
Yes. Okay, because the only available launch vehicle from Europe really is an Ariane 5, which is a huge rocket and it's very expensive. But if we could use it, it would be great. But we were trying to constrain to a lower price. Okay, and the price of this launch vehicle is half what the Ariane 5 is. And the difference, so it's $80 million versus $150 million. It's a significant amount of money. So compared with that, then the mirror diameter doesn't seem like too big a thing to give up. So this is a cutaway shell of this Y tube with these 2 payloads, and remember we have to point plus or minus a half a degree in here, and so there's a hinge at the back, and there have to be some actuators here at the front to point, to allow the distance between the angle between these 2 payloads to be varied. Okay, and we have to exchange laser signals between them, and so there'll be an optical fiber from that optical bench to this optical bench. Okay, this is just a schematic diagram of the same thing with the hinge on the back, the telescope, and the optical bench in here. So on the optical bench, there's this cylinder here forms the inner wall of that 3-stage thermal filter I was talking about. So there's the cylinder wall here. Outside of that, there's this Y-shaped tube, which is thermally isolated from this. And then the Y-shaped tube, in turn, is thermally isolated from the spacecraft. So that's the 3-stage thermal filter. We have the 30 centimeter mirror with a secondary. We're sensitive to thermal variations in this length, obviously, in our telescope. If the temperature of this change and the thermal expansion coefficient of the secondary was reasonably large, like 10 to the minus 7, then changes in temperature will cause that length to change picometers. So that sets something on the thermal stability that we need. The optical bench here, I'm going to talk about a little bit later. There's a test mass at the center inside the vacuum chamber and some optics for routing the beam around and sending it out to the back. This optical bench we think of being supported from a hoop like this, so that thermal variations, even the ones that trickle in past this inner thermal shield, kind of come to this point and then are sort of equally distributed to the 2 ends of the optical bench. The goal here is to try to minimize temperature gradient changes across the test mass housing inside there. That's just a picture of a telescope. We think we could buy one. That's changing, I guess, but I think that one would work myself. So there's the optical bench. So we have a 1-watt laser somewhere, and this light is brought in by a fiber, and the position of that end of the fiber has to be controlled. And this is simplistic, it turns out. We need to be able to adjust its angle very accurately. And so this is turning out to be a fairly complex piece of equipment. This is a collimator that just expands the laser beam from the fiber beam to something that's convenient, a few millimeters in diameter. We need a phase modulator for modulating the frequency standard, the 10 megahertz clock that we use for measuring phase. We have to be able to modulate that onto the laser beam. This may or may not be done on this optical bench here. The beam is reflected here. It's a linearly polarized beam. This is a polarized beam splitter. So 99.9% of the light gets reflected off that interface and goes out through the telescope after passing through a quarter wave plate to convert the light from linearly polarized to circularly polarized. Some of the linearly polarized light leaks through and is the reference signal for the oscillator. So the big power beam that comes out of here, which is about 0.3 of a watt, doesn't bounce off the test mass. If it did, the fluctuations in the power on the test mass would affect this too much. Light coming in from the other spacecraft is circularly polarized, just like this was going out circularly polarized, goes through the quarter wave plate, and it turns out that it's linearly polarized in the polarization that passes through the beam splitter, through another quarter wave plate and becomes circularly polarized, through this optical window into the vacuum housing that contains the test mass, off the test mass, through the quarter wave plate again, and now it's reflected by the beam splitter and comes to this photodiode. Okay, so this photodiode is measuring the local laser light that leaked through here to the incoming light that bounced off the test mass. So this signal here is one of those S1s. That's half of the round-trip light time measurement. Now on the other spacecraft there's another signal, and we can make that into a mirror-like signal by locking the laser beams to keep that at a null. So we can treat one half of each spacecraft on the far ends as a mirror if we operate it in that mode. Now there's two of these, so there's two test masses on each spacecraft, and the way we did this right now is we bounced some of the laser light off the test mass but then reference to the beam splitter. So if we just had this signal, first of all we wouldn't be able to compare it to the other arm very easily, and secondly we would be sensitive to motions of this beam splitter with respect to the test mass. So to cancel that noise out, part of the outgoing beam is picked off here and sent around the back, and then part of that is brought here, it's bounced off the test mass and then sent to the other side. So there's this, and then the light that comes through here bounces off the beam splitter and it comes to this photodiode. So think of this photodiode plus its mate as comparing the position of the test mass with respect to its beam splitter, as well as allowing an intercomparison of those lasers of the two different arms. So are you going to go into this in more detail, Bob? No. I'm not.
I think I'm going to emphasize the details of the simplest part of it rather than mechanics and quarter-wave fluctuations.
That's a good.
I'll have equations.
Okay. I don't like equations. I like pictures. Okay. So that's the general optical path. If there's no questions on that, I'll just skip on, but you can come back to it.
What do you change the polarization? Oh, is it just the way?
We have a linearly polarized laser. So I think of the laser beam as being polarized in this direction, transverse to the beam. And when it gets to here, it goes out. And when it goes through a quarter wave plate, it converts from linear polarization to circular polarization.
What's the reason for this? Why do we want to change it?
Well, we want some of the incoming light to go off the test mass, and we don't want the outgoing light to go off the test mass. And so we need to... I don't know, I think we just lose part of the light. If we used unpolarized light, Bob, and this was an unpolarized beam splitter, then half of the light would come through on this photodiode. That'd be a huge effect, right? So we'd have 1 watt of laser power here, which is not necessarily what we want. And we'd have half a watt going out there, right? So we've lost half of our laser power.
I mean, you want to separate the local oscillator beam from the signal beam. And this is a way of doing that without giving them spatial separation. There's advantages to having the beams overlap. They're just coded by polarization as opposed to separating the spatial.
But our incoming beam is Doppler shifted, so we know the incoming beam is different than the local beam. So if the incoming beam just goes through this unpolarized beam splitter, half the beam will be lost here. When it bounces off again, it comes through here, half of it will be lost again. So we'll only end up with a quarter amount of the incoming light. All right, so we would lose a lot of the light power.
You could do it without the polarizer.
But I think you could do it without the polarizer. Okay, I think the polarizing optics or maybe more useful for when you don't have the Doppler shift and you can't tell scattered local light from incoming light. Okay, the rate of change of the arm lengths causes a Doppler shift, which is a nuisance in terms that it causes a noise. On the other hand, it simplifies things that we can tell the incoming signal from the outgoing signal fairly easily. So that's an advantage. Okay, thermal stability. We need thermal stability. Why do we need thermal stability? The biggest reason that we need thermal stability is that changes in temperature will cause force changes on the test mass. Any constant force we don't care about so much, but changes in force are things that will look like signals. So it'll be hard to tell gravitational waves from that. But a DC force we're not so worried about. So it's the changes in temperature that matter. And so temperature affects the force on the test mass through thermal radiation pressure, just the fact that the test mass is looking at a surface. So there's thermal photons going back and forth between them. And if those surfaces change in temperature, that will change the force on the test mass. And also through the radiometer effect if there's any residual gas left around. We also care about optical path length changes. We have this beam flying around this inner optical bench. If you compare the front of the beam to the back of the beam to the other optical bench on the other payload arm of the Y arm and back again. So we need those lengths to be stable at the 10 picometer per root hertz level. So we need that optical bench to be made out of an ultra low expansion material with a low thermal expansion coefficient. The fiber going between the spacecraft, we have an outgoing and an incoming beam, so that's canceled to some extent. But we want that temperature to be relatively stable. And then the secondary mirror from the primary mirror spacing, if that changes, that will also look like a path length changes. So there's lots of sensitivity to thermal noise. And the solar luminosity is the dominant source of power variation. We've done some detailed thermal analysis, and we'll be doing more. It turns out spacecraft equipment, if it's running at a power level about a part per thousand, is a typical power variation for spacecraft equipment. And the solar luminosity changes are large compared to that. The solar luminosity is 1,350 watts per square meter on the spacecraft, and the fluctuations are at a millihertz, or about a part per thousand of that. So we really want to filter that down because we want to end up with sort of microkelvin stability on the inside.
These fluctuations, is this from flaring events, or is this just kind of global solar luminosity change that you're worried about?
It's a global luminosity change. It's not a flare event. I don't know if it's due because of waves, you know, with modes of oscillation of the sun, or whether it's sunspots and they rotate with time. I don't know the source of them. They're noise to me. I just have to get rid of them. There is some concern that modes of oscillation of the sun that have mass redistribution will cause signals that look like gravitational waves, and so that is something that people worry about. But I haven't heard anybody worry about the source of the luminosity changes. Sorry. Okay, so how much do we really expect it to change? This is analysis that we did some years ago. At a millihertz, we need the temperature to be stable to about a microkelvin per root hertz. Is the number that we usually use. And in our analysis, we usually get much better than that at a millihertz, by about a factor of 100 or so. The telescope is not insulated as well as the optical bench because it's not mounted from this hoop arrangement where the optical bench was mounted from inside the support cylinder. So it sees more temperature variation than the optical bench, but it's still pretty good. And we haven't really worked very hard at optimizing the thermal isolation system. We've assumed fairly conservative numbers in terms of reflectivities of surface and things like that. So getting the thermal stability that we need, we think can be achieved. There was a very nice experiment done by Michael Peterson at the Max Planck Institute, where he took an optical cavity, which is sort of the size of an index finger, made out of this ultra-low expansion glass, and he surrounded it by these gold-coated shields, very much like we're going to have the 3-stage gold-coated materials for LISA for the thermal isolation. In the pictures of the spacecraft, everything is different colors so you can see it. But in practice, everything will be gold-coated, and it'll be as hard to tell apart as things in here. And then he put it inside the vacuum chamber. So he actually had 2 different vacuum chambers, each with this thermal isolation system with the separate cavities inside them. And what he did then was he locked a laser to each of the 2 cavities and then compared the frequency of the 2 lasers to measure how good he could stabilize a laser. And so this is a measure of frequency So the measurement was frequency in hertz, and so the power spectral density is in hertz per root hertz. This is the unstabilized laser. A free-running laser has a lot of frequency noise to it. So we've been assuming 30 hertz per root hertz as the noise for the laser that we're going to have to cancel by a factor of 1 billion or so between the two different arms. And this is what he actually measured when he compared the outputs of the two laser signals, stabilized to these two different cavities. And so to millihertz, he actually got right around that millihertz or this 30 hertz per root hertz that we've been thinking about. This was the shot noise limit, and this was some error signal. What's the error point signal, Don?
Well, it's before the gain, so that's what gets suppressed by the gain.
Okay. Anyway, this is the important number. Sometimes I just delete that curve since I can't explain it. Okay, but this is what's important. So he's got that thermally stabilized cavity, so you can say, well, how stable was the length of the cavity? You know how stable the frequency was because you measured the frequency stability. If you know the length of the cavity, then you can figure out how stable the length of the cavity was. And so the length of the cavity was varying by less than 10 to the minus 14 meters per root hertz, right, over the frequency range of LISA interests. And so some people, like Brzezinski, have worried that you'll have low frequency noise in your optical bench that will cause noise as it creaks and groans around. And at least in this case, that didn't happen. Okay, so we had stability that was small compared to the picometers per root hertz we're looking for the laser, for the LISA stability. So this is an interesting result. And then if you say, well, I know the length of the cavity, I know the temperature expansion coefficient, how stable was the temperature stability was this. And so it's better than microkelvin per root hertz, which is what our requirement is, but not by that factor of 100 that I showed you. And I think that's because the laboratory environment thermal fluctuations are bigger than the solar thermal variations that we're expecting. So I think everything is consistent to show that we can get this microkelvin per root hertz stability. This is really a very nice experiment. Okay, and then in the same experiment, he measured what the stability of the laser power was. So I said that the output power, the output laser beam does not get reflected off the test mass, but a fraction of the output power does get reflected off the back of the test mass for comparison to the other bench. So any fluctuations in that power will cause a variation in the photon pressure on the test mass. And so the stability we need on the power to get to 10 to the minus 16 meters per root hertz is whatever this is, 10 to the minus 4 fractional power stability per root hertz. So there we've normalized by the power. Okay, and he's getting better than that. Okay, so now I'm going to segue from interferometer noise into test mass noise. We have these test masses which are our reference for the distance measurements, and we need to protect those test masses from external forces like solar radiation pressure, etc. So the idea is to have a test mass like this gold sphere, which is inside a cavity, and have the spacecraft rigidly mount to that cavity, but somehow measure the distance between the sphere and the cavity so that if atmospheric drag, say, in low Earth orbit, pushes the spacecraft back towards the freely floating test mass, this distance will start to shrink. Okay, so if you can measure that distance change, then you can fire these rockets to speed the spacecraft up so the atmospheric drag won't push the spacecraft into the test mass. So this was originally done in 1972 by the Navy to try to launch a perfectly gravitational-only spacecraft in low Earth orbit to be used as a navigation reference for ships. And so far, this is the only time they've done that. It's the only drag-free spacecraft that's been flown so far. And that's partly because the Navy decided, well, this is pretty silly. Why don't we just put a lot of good clocks in orbit, all right, and measure round-trip light times, and then we can know where we are instantly instead of having to know where all these spacecraft are and things like that. So this has been the only time this has been flown, was this Triad mission. So the position measurement that's used to measure the position of the test mass with respect to that housing was capacitive. Just measure the change in capacitance between the sphere and the wall of the test mass as a measure of the position. You could do it optically, and optically you'll get much smaller noise, and this is a subject of much debate, but there's a lot more heritage with the capacitive sensing, so the capacitive sensing is the nominal choice. Okay, and now let's talk about the geometry of the test mass. Gravity probe B is going to have 4 spherical masses which are spinning, and they'll be inside spherical cavities that have these little circular electrodes. Okay, and so the electrodes are used to measure the capacitance of the sphere with respect to them, and that way they can measure the position of the spacecraft with respect to the sphere in all 3 degrees of freedom by using those capacitance sensing. The primary measurement for gravity probe B is the spinning. How fast is it spinning and what's the direction of the spin axis, and that's actually read out using a superconducting squid loop, which we're not going to use on LISA. So the performance of this spinning sphere as a test mass will be measured by gravity probe B, hopefully once it launches, and its launch date is now not October 2002 but January, I think, of 2003. But once it's launched, we'll be able to get some idea of what the performance of those 2 spherical test masses as position measurements can be done. An alternative to the spherical geometry is shown here. This is the test mass that is used for accelerometers that have been developed by this French company Onara for measuring the acceleration on the spacecraft. And so for the GRACE mission and for a couple other missions, rather than flying drag-free, adjusting the spacecraft position based on the position measurement, they actually just measure the force on the test mass needed to keep it centered, to measure the force on the spacecraft and take that out as a calibration. The reason that we don't want to do that for LISA is the limit on that system is how much force you apply and how quietly you can apply that force. Introduces noise, the application of that force. And so that's not nearly as good in terms of minimizing the forces on the system as flying a drag-free system. But there's a lot of work has gone into this, and so it's actually this device that's been used as the basis of the LISA test mass system. So we sort of have the choice of the sphere versus the cube, and the sphere has this really nice property that you don't have to control its angular degrees of freedom. It's just there, and you hit any part of it, and you should be equidistant from the center of mass, and that would reduce the number of control systems we had on the spacecraft. The problem is, if you try to bounce a laser beam off a sphere, well, it's not perfectly spherical. And since it's spherical, mostly spherical, you can't control its position, so you can't control whether the laser beam hits this bump or this bump or this bump or that dip. So the spheres that were done for gravity probe B, which are the smoothest spheres ever made, are rough at the nanometer level. And we're trying to measure at the picometer level. And so we're concerned about the smoothness of the surface. If we spin the mass and average over the spinning, we might be able to do it. But the problem, if we had an orbit that was always in the fixed plane, so we're always averaging over the same point, that would be nice. But because the LISA orbits are varying in this tilt once per year, that means if your sphere is spinning like this, the laser beam is going to hit here part of the year, and then 6 months later it's going to hit down there. So it's going to be always moving in latitude as a function of time over the sphere. So even the spinning doesn't average everything that we need to do. So we just don't know if that's going to work, and we don't know how to test it even if we thought it would work, because it would require a 2 spacecraft experiment probably to validate. So we've gone to the cube, which the cube has the disadvantage.
How big is the laser component this year? Like how big is the region where you operate on?
The spot of the laser beam size is something convenient like a millimeter or a few millimeters in diameter, and the test mass, this test mass, is sort of 4 centimeters by 4 centimeters by 6 centimeters. That's this one. So the beam is big compared to the displacements, but there's some average position, and that average changes as you move over different parts of the sphere.
How do you increase the size of the beam?
How do we? You can have any beam size you want, and in fact, we looked at this a little bit. If you had a spherical test mass, you would want to focus the beam so it would come to a point at the center of the sphere. That has maximum insensitivity to the interferometer readout for displacement of the sphere position. However, we're more inclined to do cubical test mass so that we can control which part of the test mass that the laser beam hits off of, and we can lap very flat to have a very good optical surface. The disadvantage then is we have to have control systems to keep that oriented properly. But this is an example of such a device that's actually been built at Onara, and they've got this test mass with holes through it to make it lighter. And the reason they went to that original very flat test mass was so they could apply voltage and levitate it on the ground. And that's very advantageous for testing. However, you're trying to minimize displacements that are due to things other than gravitational waves. it's better to have a heavy mass, as heavy as possible, so the forces don't move it around so much. Okay, so this is a compromise where they've made a bigger shaped mass, but with holes in it to make it lighter, so they could do some ground testing.
Isn't it easy to make cubical smooth object? Because you can just make something like I'm just thinking maybe you could make something like a monocrystal.
Like a
monocrystal?
Oh, I can't hear that.
Monocrystal.
A monocrystal. Well, a monocrystal might not be cubical, but you could polish it into a cube. Well, we're normally using a cubical type structure. Okay, and the disadvantage of the cube, the advantage of the cube is you can polish it very smooth, and you can control its position and attitude so the laser beam always hits the same spot. The disadvantage is you have to control the test mass so it always hits the same spot, and so you have to worry about noise introduced by doing that. Okay. The other point is that we have laser beams going in two directions, and that angle changes as a function of time. So if we use a cubical test mass, we can't bring beams from both spacecraft and have it be normal to both faces of the cube, because it doesn't change as a function of time. So that's why we have two cubes, is so we can have two different pointing directions. That means we have to push the test masses around to account for the pointing fluctuations. All right, so it's a more complex system than if we had a single sphere.
Also, I'm not sure there's a material from which you could make a monocrystal that would have high density and very low magnetic susceptibility.
I don't know the magnetic susceptibility of quartz, for instance. But quartz is probably not good. But
It's definitely not as low as.
how about sapphire?
That would be costly, but it might work.
Sapphire's cheap compared to gold, platinum. We're going to use a test mass that's 70% gold, 30% platinum. And that's because gold is diamagnetic and platinum is paramagnetic, or the other way around. And if you mix them in the right ratio, then you get a non-magnetic material. And so you have fewer magnetic forces acting on the test mass that way. And that material is not so cheap. All right.
So is there no advantage to using something like a cylindrical shape, where the long axis is transverse to
the cylinders, if our orbits were always in the same plane, then a cylinder I think would have some advantages. But because we're tilting, I think optically that's not a good geometry to use. I guess we could rotate it. I have to think about that one.
That's what Step is using, right? I mean, they have one cylinder to stick leather in there.
They use concentric cylinders so their centers of masses coincide, right? And that's not so important for LISA. For the equivalence principle, where you're looking for the difference in gravitational attraction of two different masses, that's important. All right, there's a lot of different forces that act on the test mass, and I'm running out of time here. So Bonnie's going to talk all about this later anyway. So just to give you some idea, there is some reason to think that the level of forces that we need can be achieved. Okay, and there's various types of noise. Position-dependent noises are an important one. The gravitational attraction from various different masses on the spacecraft is an important source of force on the test mass, because it's hard to get the spacecraft mass distributed just exactly so that there's no force at where the spacecraft, at the test mass position is, and then there's no gradient, there's no sensitivity to motions of the spacecraft relative to the test mass. Because remember, the spacecraft can be pushed by forces. We're going to have to measure what that pushing is and push back against it. So there will be some displacements of the spacecraft relative to the test mass. So unless we can make the gravitational gradients exactly balanced so there's no change in gravitational force on the test mass, then we're going to have a problem. So 1 kilogram mass, 10 centimeters from the test mass, gives a gradient of 10 to the minus 7 meters per second squared per meter of acceleration. And if the spacecraft is jittering by 10 nanometers per hertz, then the product of these will be the amount of noise we want for the LISA mission. So achieving the sensitivity curve that I showed back at the beginning means we have to get the masses balanced to this level, so we have to know where every kilogram is to 10 centimeters or so and choose them appropriately so that we don't get any worse than that. And we have to control the spacecraft position to 10 nanometers per root hertz. Patch fields, which Bonnie will talk about. It's so nice to have you coming later, Bonnie. It's another thing that has a position-dependent noise. There's a Lorentz force. The test mass gets charged, and it's moving in the sun's magnetic field. The sun's magnetic field is not constant. It varies from point to point, so a moving test mass that's charged moving through that magnetic field will have a significant force on it. Gravity Probe B has developed this technique for knocking the charge off a test mass by shining ultraviolet light on it to keep this force on it small, and we plan to do that. Magnetic forces on the test mass we plan to have small by having this gold platinum material, the most expensive thing we can think of. I know, I got 5 minutes. I'm just about done. I could stop at any time. Okay, gas pressure and thermal photon pressure, these are related to the thermal stability that I talked about earlier. Okay, so how far off are we from getting the level of acceleration noise that we think we want for LISA? For distance noise, we want to measure 10 picometers per hertz, and that's clearly been done for Michael Petersheim's cavity experiments already, so the technology for doing that is in line. The best acceleration noise measurements that I know of are from Onro, where they've taken 2 of their accelerometers and put them on this pendulum bed and compared them. They actually controlled the orientation of this pendulum based on the readings of one accelerometer and read out the noise forces on the other one. And they got sort of this 10⁻⁸, 10⁻⁹ meters per second squared per root hertz. This is what that's supposed to say if it were legible. So that's the best ground test that I know of for measuring the performance. Another ground test that you could think about is a torsion balance experiment.
Hold on a second.
Okay.
Just want to look at the technology production can go even around 5 minutes or 10 minutes of
I'm almost done.
So you just not the other places, okay?
I'll wrap this up pretty quickly. For the Etwash experiment for measuring the equivalence principle, they have these different masses on a torsion pendulum, and the angular noise on that is pretty good. You know, it's 10 to the minus 9, whatever. This is milliradians per hertz. So the angular noise is very good. And if you figure out what the force on that test mass would be to correspond to this rotational noise, if there was a force in a transverse direction to get this kind of rotational noise, and if you divide it by the mass of the LISA test mass, instead of these are much lighter than the LISA test mass. But if you divide it by the LISA test mass based on what force they can have, then that would set some kind of measure at 10 to the minus 13 newtons per root hertz. So that's within a couple orders of magnitude of what the LISA goal is. But this is not really the LISA mass or the LISA geometry, but it gives some kind of hope of doing that. But we still want a factor of 100 times better than that. I'm going to skip this. Okay, to do the drag-free control on the spacecraft, let me come back to that. To get the level of force noise that we need to prove that we can do it, we're going to have to fly something in space if we have to prove it ahead of time. And that's what we're currently planning to do. To do the spacecraft control, we need to be able to control the spacecraft position with an accuracy of 10 nanometers per root hertz. And to do that, we're going to need a new class of thruster that can move the spacecraft very, very, very finely. The total force that on the spacecraft from the solar radiation pressure, which is the maximum force the thrusters have to apply, is about 20 micronewtons. And how many fractions of a sheet of paper that is about equal to the weight of a Post-it bomb.
Actually, the hole would punch out of a sheet of paper.
All right, the hole punched out of a sheet of paper, the weight of that hole of paper, that's the maximum amount of force we have to exert against the sun. And we need to be able to control the thrust with about part per thousandth of that, okay, in order to get the spacecraft positioned to 10 nanometers. So there's 2 classes of thrusters that are being investigated for this. One is it's called a FEEP thruster, field effect emission propulsion, where there's a liquid metal that's drawn up a capillary. There's a high voltage here that tends to ionize an atom at the tip of the surface and then extract it and eject it. So it's a way of getting an output of cesium ions, right, which are atoms that are positively charged, and sending them out at a velocity that's controllable by adjusting the voltage. So you can get a very, very fine level of thrust. There's a positive charge being given out then, and you don't necessarily want the spacecraft to accumulate a lot of negative charge, and so there's a neutralizer to send out electrons to counter that. This thing, 19 millimeters, 2 centimeters, is actually flown. This is a cylindrical version of this. This is a slit version. This is the Italian version. This is the Austrian version. This is actually flown on the cluster spacecraft, an Earth observing spacecraft, and there its goal is to actually spew out positive ions to counteract positive ions that are collected by the spacecraft to maintain a neutral charge. So that's one class of thruster. And another class of thruster uses a fluid propellant and then an ionization process very much like the liquid metal ones. Measuring the performance of these thrusters on the ground is not particularly easy because we have to measure fractions of this little hole of paper. But using a torsion balance, there's been some recent experiments with the colloidal thrusters that look very good. It looks like they should meet our goals. And I'm going to end with this slide. To prove that the noise on the test masses is as small as we need it to be, which is a factor of 1,000,000 better than has been demonstrated so far on the ground, but maybe a factor of only 100 to 1,000 better than we could do on the ground, we're going to fly an experiment in space where we have a spacecraft flying drag-free around one test mass and measure its position with respect to a second test mass with the laser interferometer. And hopefully this distance will remain constant enough to infer that the forces on the test mass as a function of time will give us the force noise that we need to go along with the shot noise that we're shooting for to get the sensitivity that Lisa needs. So this is the next step that I'm working on, is to fly this experiment to show that the force noise is small enough. And then the other developments that are really needed are to show that the interferometry works in all degrees of freedom, the laser stabilization, the clock noise, the pointing noise, all that has to be demonstrated at some level before you fly a $1 billion space mission. And then we have to get the $1 billion. Okay? Other than that, there's no problems. Okay, I've used up my hour and a half. I hope you've learned something about the concept, and there'll be a number of talks coming up about specific details. I'll take any questions, or class is over. Class is dismissed.
You keep saying you're all supposed to be in the class tonight for dinner, right?
Sorry?
You keep tell them they're all supposed to be in the class for dinner tonight.
I don't remember that.